Hello, I'm Ethan J. Armis, and this is the Physics 2211 Lab 2 report. This lab was constructed for the purpose of observing an object falling in ideal conditions with and without the effects of air resistance or drag. The important formulas used are Newton's second law, also called the momentum principle, which is defined as the change in momentum over the change in time, where change in momentum is defined as the change in velocity times mass. This can be rewritten as the velocity update formula. We also use the position update formula and the formula for the force of quadratic drag. It is called this because the magnitude of the force is proportional to the square of the speed, and it is defined as negative c times the magnitude of the velocity squared times v hat, the unit vector of v, where v is velocity and c is some coefficient of drag specific to the falling object. And we also use the force of gravity, where the acceleration due to gravity, of course, is 9.8 meters per second squared. In the real world, objects face air resistance, so the force of drag factors into the net force. By the end of the lab, we'll be able to see how significant this force is based on the computational models. In the lab, the system is the falling disk, and its surroundings is Earth because of gravity, and air because of the air resistance. The disk is initially starting at a resting condition, and it is then released and falling out of frame and out of the video with a non-zero velocity. The lab involved us recording this process and then putting it into Tracker to gain data about its position and velocity over time. And then we used that data in the formulas defined before to create two computational models, one that involved drag and one that did not, to approximate the situation that we recorded. At the end of the experiment in creating the two computational models, there were differences between the data acquired from the actual results and the computational results when there was no drag. Accounting for drag involved putting the formula for drag into the calculation to find the net force, where the coefficient for it I deduced to be negative 93 for my computation. Here is my data. You can see that the data for the computational model that accounts for drag is very similar to the data from the actual experiment, whereas the computational model without drag shows the object continuing to accelerate downward, covering more and more distance as time goes on. Now, the model with drag is not completely accurate to the actual experiment. Possible sources of error include an inaccurate drag constant, as well as a tracker reference error, like not putting on the exact right frame. And also, I noticed while composing this lab report that the code had an initial velocity for the falling object at -1 instead of 0. So that would definitely be a factor into the sources of error between those two data points. Here is my code. This is the same in both models. And then here are the two different versions for the two different models, one with drag and one without. The what if question asks how would the terminal velocity change if the object was thrown downward rather than dropped from rest. The initial velocity has nothing to do with the terminal velocity of a falling object, so the terminal velocity would be the same in both cases. In my computational model, the object reached a final velocity approaching negative 1.75 meters per second. I then altered the code to give it a much greater initial velocity of negative 100 meters per second. And it ended up approaching the same final value of negative 1.75 meters per second. If a falling object is moving too fast, drag will slow it down, and if it's going too slow, gravity will speed it up. Terminal velocity is when the force of drag is equivalent to the force of gravity, and they cancel out. Here is a better look at those two graphs where you can see that they approach the same value of negative 1.75. And then here, the what does it mean is talking about what is terminal velocity and what does it have to do with the net force and which model can predict the terminal velocity. The model with drag predicts the terminal velocity because one could find the acceleration at which the falling disk is slowing down and calculate the upwards and downwards force until it cancels out. Using this, we can find the change in velocity and change in time and predict when terminal velocity is achieved. We know we have reached terminal velocity once the net force evaluates to 0 because, again, the upwards and downwards force between drag and gravity would cancel out. The object will still move, however, with the velocity, which would be constant as there's no more acceleration. In conclusion, this lab demonstrates the interactions between objects and their forces of their surroundings, particularly the inherent properties of an object in free fall and its interactions with air resistance. Drag is a powerful force, often overlooked in physics problems, so this lab is unique and offered a chance to explore this. Thank you.